All right, in this section, we're going to be looking at what complex numbers are and how to evaluate expressions that have complex numbers in it. And we'll be adding and subtracting complex numbers, multiplying complex numbers, dividing complex numbers, and also performing operations that contain square roots of negative numbers. We'll first define what the imaginary unit is. An imaginary unit, which is called I, is going to be defined as the following. I is equal to the square root of negative 1, where I squared is equal to negative 1. Okay, so I will be the square root of negative 1. And that will mean that the square root of negative 1 would be I. And that's what we call the imaginary unit. And when we use the imaginary unit I, we can express the square root of any negative number as a multiple of I. In this example, we have the square root of negative 25. Okay, now, usually on a calculator, if you try to do the square root of negative 25, you would get an error message because there is no real number that's squared that would give you an answer of negative 25. So we can express this using the imaginary unit. So the square root of negative 25 can be broken up as the square root of negative 1, because there is a negative sign in front of the 25, and then multiplied by the square root of 25. And of course, the square root of negative 1 is I, so we write the I and then bring over the square root of 25. Now, of course, 25 is a perfect square. We can take the square root of 25, which will be 5. So in this case, you'll end up with 5i. So the square root of negative 25 would be 5i. Okay, now with the imaginary unit, we use that with complex numbers. Okay, now the set of all numbers in the form of a plus bi, where with real numbers a and b, and I being the imaginary unit, that's called the set of complex numbers. So all complex numbers will be in the form of a plus bi, where a is the real part and the b, which is the number in front of the I, is the imaginary part. Now, if b is not equal to 0, the complex number is an imaginary number. And any imaginary number in the form of just bi is called a pure imaginary number. Like in 5i would be a pure imaginary number because there's no real number added to the imaginary part. And a complex number is said to be simplified if it's expressed in standard form a plus bi. So a plus bi is the standard form for complex numbers. And if b is a radical, then usually we write the I before the b, like in this case here, 7 plus 3i squared root of 5. Here the I is going to be in front of the radical. That's to avoid any type of confusion that the I would be underneath the radical. So to avoid that, we put the I in front of the radical. Okay. And the equality of complex numbers is just simply if a plus bi is equal to c plus di. That's only if and only if a is equal to c and b is equal to d. This is basically the equality of complex numbers. Okay. Now first we'll look at how to add and subtract complex numbers. In this case here, if you have a plus bi plus c plus di, when we add those two complex numbers together, we add the real parts together, that's the a plus c, and then add the imaginary parts together, bi plus di, which is going to be b plus d, and that sum is going to be multiplied by I. So basically, you're just simply combining like terms when you're adding complex numbers. And the same holds true for subtracting complex numbers. If you have a plus bi minus and then c plus di, we subtract the real parts and subtract the imaginary parts. Okay. Or another way you can think of it is this. The minus sign will change the sign of each and every term in the second complex number when you remove the parentheses, and then you can combine like terms as well. So here we're going to look at one of the examples that deals with complex numbers, like this one. Let's say we want to add or subtract as indicated. In part A, we're going to add 5 minus 2i and 3 plus 3i. And then in B, we're going to have 2 plus 6i minus 12 minus I. Okay. So here we're going to do part A first. The 5 minus 2i plus 3 plus 3i. Now, if you want to, the plus sign is going to make everything the same. So you can do this without parentheses. Just say 5 minus 2i and then plus 3 3i. And then we can combine like terms here. The real parts we can add together, the 5 and the 3. That's 5 plus 3, which will give you 8. And then the imaginary parts, negative 2i plus 3i. Negative 2i plus 3i, that's going to give you a 1i. But of course, 1i, we can write that as plus I. And that's all there is to it. So here, the sum of those two complex numbers here will give me 8 plus I. Now part B is subtracting two complex numbers here. We got 2 plus 6i minus 12 minus I. Notice the 12 minus I is in the parentheses. Now in this case here, I can remove the parentheses here in the first one. That's 2 plus 6i. But here the minus sign is going to change everything inside the parentheses to the opposite. So the minus sign will make the 12 minus 12. And this minus sign will make minus I plus I. So now I got 2 plus 6i minus 12 plus I. And then we go ahead and combine some like terms here. Let's see. The real part, 2 minus 12, that's going to be negative 10. And then 6i plus I, or 6i plus a 1i, that give you plus 7i. So here you're going to have negative 10 plus 7i. Okay. So this is how you would add and subtract complex numbers. All right, next we'll look at how to multiply complex numbers. When you multiply complex numbers, that's performed the same way as multiplying polynomials using the distributive property and the FOIL method. Now, when we multiply complex numbers, any occurrences of I squared, we're going to have to replace that with negative 1. Because of the fact that I is going to be equal to the square root of negative 1, where I squared equals negative 1. So any occurrences of I squared, you must replace it with negative 1. And we're going to look at a couple of examples that deal with multiplying complex numbers. All right, now let's take a look at these two. Here we got 7i multiplied by 2 minus 9i. Now notice in that one we have a pure imaginary number multiplied by a complex number. So we know we're going to have to use the distributive property. Now in part B you got 5 plus 4i times 6 minus 7i. Here you got two complex numbers multiplied together, so you're going to have to use the FOIL method. Alright, but let's look at part A first, and then we'll look at part B. Here we got 7i multiplied by 2 minus 9i. A pure imaginary number multiplied by a complex number means we need to use the distributive property. we're going to do 7i times 2. That's 14i. And then 7i times minus 9i will be on minus 63i squared. Here, 7 times 9, that's 63, and then you got I times I, that's going to give you I squared. Now, if you recall, we replace any occurrences of I squared with negative 1. So here's what I'm going to do. I'm going to rewrite this as 14i minus 63 times negative 1. Okay, because I squared is negative 1, so you're going to replace that I squared with the negative 1. And then simplify. This will be 14i plus 63. That's minus 63 times that negative 1 will make that a plus 63. So you got 14i plus 63. Or you can say 63 plus 14i, which is the more appropriate way to write it because, of course, standard form is always the real part plus the imaginary part. The real part goes first, followed by the imaginary part. Now, part B, we got 5 plus 4i times 6 minus 7i. And in this case here, we want to multiply those two complex numbers together. And to do that, we're going to have to use the FOR method. And the FOR method is this. We multiply the first terms, that's 5 times 6, which is 30. And then the outer will be 5 times minus 7i, which will be minus 35i. Then the inner will be 4i times 6, which will be plus 24i. And then the last term, 4i times minus 7i, which will be a minus 28i squared. Because 4 times minus 7 is minus 28, and then I times I, that's I squared. Now let's simplify this, because we know we're going to have to replace the I squared with the negative 1. So here I'm going to bring down the 30. I'm going to go ahead and add negative 35i to the 24i. That's going to give me a minus 11i. And then minus 28 times. And here I'm replacing the I squared with negative 1. So I have minus 28 times negative 1, which will give me a plus 28. So we'll say 30 minus 11i plus 28. And if you add the 28 to the 30, you're going to get 58. So that'd be 58 minus 11i. Okay, and that's my answer in standard form, 58 minus 11i. All right, so far we talked about how to add, subtract, and multiply complex numbers. Now let's look at the next thing, or the next operation of complex numbers, which is division. And to divide complex numbers, we're going to have to use what they call the complex conjugate. And in this case here, the complex conjugate is of the number a plus bi will be a minus bi. It's just simply changing the operational symbol in the middle to the opposite. So if you have a plus bi, its conjugate would be a minus bi. And if you have a minus bi, then its conjugate would just simply be a plus bi. Now if you multiply complex numbers, complex conjugates together, you're going to get a real number. Like with this one, a plus bi, and if you multiply that by a minus bi, you're going to get a squared plus b squared. Okay. Now you can do the FOR method on this if you like. And you're going to see that the middle terms will cancel, and then I squared, of course, is negative 1, which will make minus b squared a plus b squared. So you'll get a squared plus b squared. And similarly, a minus bi times a plus bi will also give you a squared plus b squared. So simply, it's always going to be the square of the first term plus the square of the last term. Okay? Because this is like the sum and the difference of the same complex numbers. let's look at, well, before we look at an example, let me mention this. Complex conjugates are used to divide complex numbers. By multiplying the numerator and the denominator, you will obtain a real number in the denominator. So if you multiply the numerator and the denominator by the same complex number, or the complex conjugate of what's in the denominator, you're going to get a real number in your denominator. And let's look at a couple of examples, like this one. We have 3 minus 4i divided by 4 plus 3i. And we want to divide and express the result in standard form. Okay, so here's the problem that we're looking at. 3 minus 4i divided by 4 plus 3i. Now, let's look at our denominator, which is 4 plus 3i. The complex conjugate of 4 plus 3i will simply be 4 minus 3i. So we're going to multiply the numerator and the denominator by 4 minus 3i. Okay, I'm just simply changing the operational symbol in between the two numbers to the opposite sign. And then we're going to multiply straight across. We're going to multiply numerator times numerator and denominator times denominator. Now the numerator, we're going to have to use the for method. And in this case here, if we do 3 times 4, that's going to give you 12. And then the outer will be 3 times minus 3i, which is minus 9i. The middle, well, the inner will be negative 4i times 4, which will be a minus 16i. And then the last term, negative 4i times a minus 3i, will be a plus 12i squared. And all that's over. Now, the denominator. You got 4 plus 3i times 4 minus 3i. Those are complex conjugates. When you're multiplying those complex conjugates, you're going to get a real number. And in this case here, you can do the for method, but the quick way to do that is to simply square the first term, which is your 4. So 4 squared will be 16, plus the square of the second term, or the coefficient of I, which is 3. Square that, you're going to get 9. So your denominator will be 16 plus 9. Now again, you can use the for method in the denominator. You'll find out that the middle terms will cancel. And then minus 9i squared, and of course I squared is negative 1, and that'll give you a plus 9. Now in the numerator, we're going to have to simplify this. That I squared is negative 1. So here I'm going to have 12. I'm going to go ahead and do this. Minus 9i times, minus 9i minus 16i is minus 25i. Combining like terms here. That negative 1 will make that plus 12 minus 12 divided by 16 plus 9. That's 25. And here in the numerator, these 12s are gone. I'm left with negative 25i divided by 25. And that's simply going to be negative I. Okay. So here, when you simplify this, your final answer, of course, will be simply negative I. All right. Now I'm going to do another example that deals with complex numbers, or division of complex numbers, like this one. Here we want to divide and express the result in standard form. In this case here, we got 5 plus 4i divided by 4 minus I. 5 plus 4i divided by 4 minus I. Okay, so here we're going to simplify this through dividing using complex conjugates and express in standard form. The denominator is 4 minus I. The complex conjugate for that will be 4 plus I. So we're going to multiply the numerator and the denominator by 4 plus I. And we're going to go ahead and simplify. Well, just multiply numerator times numerator, denominator times denominator. So the numerator, we're going to have to use the FOR method. And in this case, 5 times 4, that's 20. The outer is 5 times I, which is plus 5I. The inner is 4I times 4, that's going to be plus 16I. And the outer is 4I times I, that's going to be a plus 4I squared. Now the denominator we have nothing but complex conjugates that are being multiplied. 4 minus I and 4 plus I being multiplied. So the quick way of doing that will be squaring the first term. The first term is 4. Square that, you're going to get 16. And then plus, the coefficient of I is a 1. So we square 1. 1 squared, of course, is 1. Now let's simplify this part up here. The I squared, of course, is negative 1, which will make that 4 a minus 4. So now we're going to have 20. I'm going to add 5I and 16I. That's going to be a plus 21I. And this minus, the negative 1 will make that plus 4 minus 4 because of the fact that I squared is negative 1. Then 16 plus 1, that's going to give me 17 in the denominator. Now let's simplify this. 20 minus 4 is 16 plus 21I over 17. Okay, now we're going to break this up as 16 over 17 plus 21 over 17 times I. And that would be your final answer to that particular problem. Okay, so that would be how you would divide complex conjugates. All right, the next thing we'll look at is roots of negative numbers. And we'll talk about the principal square root of a negative number. For any positive real number called b, the principal square root of a negative number, which is negative b, is going to be defined by the square root of negative b equals to I square root of b. Okay, so if you have the square root of negative b, you take the principal square root of that, which would be I square root of b. And when we perform operations with square roots of negative numbers, we begin by expressing all square roots in terms of I. So the first thing you do, if you have negative numbers underneath the radical, express those as square. All those square roots has to be expressed in terms of I first, and then you take the square root of that particular number. Okay. Now next is just the table of perfect squares up from 1 through 10. Okay, so if you're not familiar with the perfect squares, this is the table for that. And this is only goes up to 10. Okay, I do have other examples. Let's use this one. So let's look at how we can express this as in simplest form. So here we want to evaluate these using the concept that we have to express each one as in terms of I. Here in part A, you got the square root of negative 27 plus the square root of negative 48. We'll start with that first. And then we'll get to the other two problems, B and C, later. So we'll start with that one. Now, first of all, we need to express these in terms of I. Each one of them has a negative sign underneath it. So that means negative 1 is involved. So the square root of negative 27 will be expressed as I square root of 27, and then plus the square root of negative 48 can be expressed as I square root of 48. All right, now the next step would be to simplify the square root of 27 and the square root of 48. Now 27 is not a perfect square, but it does contain a perfect square, so the only way we can do this is find the largest perfect square that can go into 27 and the largest perfect square that can go into 48. For 27, the largest perfect square that can go into 27 would be a 9, because 9 can go into 27 3 times. And then for the square root of 48, the largest perfect square that can go into 48 would be 16, because 16 can go into 48 3 times. Now you can go back and use that table of perfect squares that I showed you on the video earlier. For 27, we know 9 goes into 27 3 times, and for 48, 16 will be the largest perfect square that goes into 48 3 times, so we can use that. Okay, now, since 9 is a perfect square, we can take the square root of 9, that's 3. So now you're going to have 3i square root of 3 plus the square root of 16. That's a perfect square. We can take the square root of 16. That's 4. So that's 4i square root of 3. Now we have like terms because they're both the square root of 3. So we can do 3i plus 4i. That will give us 7i square root of 3. Okay, and this will represent the final answer to that particular problem in part A. All right, now let's look at part B. We got negative 2 plus the square root of negative 3, and that quantity is squared. All right, in this case here, we need to express this in terms of I before we do anything. So here, the square root of negative 3 needs to be expressed in terms of I because it has a negative 1 underneath the radical, so we can express this as negative 2 plus I square root of 3. And that quantity is going to be squared. Now there's a couple of ways that you can simplify this because this is a square of a binomial, or if you're not familiar with that, you can write this. You can write this product, well, you can write this expression twice because this is used as a factor 2 times. So you can write like this, negative 2i square root of 3 times negative 2i square root of 3, because that exponent tells us that everything in the parentheses is a factor twice. And then use the FOIL method. So in this case here, negative 2 times negative 2, that's the first term times the first term, that's 4. The outer is negative 2 times I radical 3, that's going to be a minus 2i square root of 3. The inner is I square root of 3 times minus 2 will be a minus 2i square root of 3. This last term times the last term, I square root of 3 times I square root of 3, that's going to be a plus. Now I times I is I square. And then the square root of 3 times the square root of 3, you multiply what's underneath the radical. That's the square root of 9. Now let's simplify this a bit. Bring down this 4. We can add these two like terms together. 2i square root of 3 and another 2i square root of 3. They're both minuses, so that's going to be a minus 4i square root of 3. Now here, this I squared is negative 1. We can evaluate the square root of 9. The square root of 9 is 3. and 3 times that minus 1 would be a minus 3. Okay. Again, I squared is negative 1, and the square root of 9 is 3. So 3 times that negative 1 will make that a minus 3. Now my like terms are 4 minus 3. That's going to be 1. So this will be 1 minus 4i square root of 3. And that's as far as I can go with that particular problem. Okay. So that's how you would evaluate part B. Now part C, we have negative 14 plus the square root of negative 12. And the whole thing is divided by 2. Okay, so here's how we will solve that particular problem. In this case here, we need to express this in terms of I, so I'll rewrite this as negative 4 plus, since it's got the negative 1 underneath the radical, that can come out as I square root of 12 divided by 2. Now, of course, 12 is not a perfect square, but we can express this as a product as two factors with one of them having a perfect square. So we need to find the largest perfect square that can go into 12. It will have to be 4. So in this case here, we got negative 14 plus I, not plus or minus, just plus, I square root of. Now the largest perfect square that can go into 12 will be 4, because 4 goes into 12 3 times. And all that's divided by 2. So you got negative 14 plus. Now the square root of the square root of 4 is 2. So I'm going to have a 2 on the outside along with the I, and then square root of 3, all over 2. Okay, now we can still simplify this a bit, because I can break this up as negative 14 divided by 2 plus 2i square root of 3 divided by 2. And then negative 14 divided by 2, that's negative 7 plus, and in this case, these 2's divide out. I'm left with I square root of 3. So my final answer there will be negative 7 plus I square root of 3. Okay, so that would conclude this particular section on complex numbers.